elections. And if anybody's interested in being on the board, we would like you to reach out to Dawn or I. You'll see the contact information in the presentation. If you'd like to be nominated for the elections, our elections will be held in November. If you'd like to be nominated, please reach out to us, and we will do the best we can to vet out the potential applicants and possibly get them onto the election slate. You must be an SCTE active member if you want to be on the board, okay? The process is nominations, then elections, and then in December, the existing board will get together with the results of the elections, and then we'll vote who is on the board for 2018, okay? From there, that board will set together the training schedule for 2018 and work with the different vendors and or the MSOs to identify what we want to train on and what are the priorities. And in turn, you will see our calendar come out for our slate of meetings. As you know, the SCTE is a not-for-profit chapter, and we essentially make money on two events: the vendor fair that is routinely held in June, and the golf outing is routinely held in May. Those two events raise money through our vendors to support the chapters on a yearly basis. So as always, I ask you to pay attention to the calendar and do what you can to support us through your management and all our vendors. Do your best you can to support us. I believe that's it. And Tom, I'll turn the floor over to you.
Great. Thanks, Peter. Today we're going to be talking about several different topics as they pertain to fiber optic technology. And we're going to start off pretty basic, talking about some of the real building blocks, the Fiber 101, and then we'll start to build on those different topics. And by the end of the presentation, I hope that you have a basic understanding of how a fiber optic network works and some of the new technologies that are emerging in fiber optics as they apply to MSO and cable TV type applications. And in addition to this presentation that we're going to be going over today, if you'd like to dive a little deeper into any of the topics that we're going to be discussing today, we have a website, and it's shown here, that will basically get you to an area where you can look at some of the other recorded webinars on Clearfield College, which is essentially, it's not a commercial or anything, but it's essentially just education that you can go to. And if you wanted to learn more about fiber to the home or WDM technology or different things like that, you can go in and listen to some short webinars that are in there as well that are recorded. So this one we will also be recording, so if you're not able to hear the audio or you miss a part of the presentation, you'd like to go back and revisit it, we will be sending out that link to Peter and the rest of the board so that anyone who misses the presentation today will be able to go back and check that out. So just to give you a quick background on myself, I have worked in the telecommunications and cable TV industry for about 15 years and have been working mostly with CWDM, DWDM, fiber to the home, and HFC type applications and fiber optic cabling. And I am a member of the SCTE North Country region here in Minneapolis and love working with the SCTE anytime I can. I think it's a great organization that really helps out their members. So if there's anything I can ever do for you from an educational standpoint or from technical specs, please give me a call. I'd love to support any chapter that I possibly can. This is going to be the agenda for today, and we're going to start off by talking about some of the basic components that are used in a fiber optic network, and then we're going to start talking about some of the transmission characteristics. In other words, what happens to an optical signal as it passes down a piece of optical glass. And then next we're going to move on to another subject, which is optical loss budgets and testing and inspection. And then we'll start talking about how do you physically handle and manage fiber and fiber cabling so that we don't have outages due to damage or any other issues that can come up from microbending and macrobending and things like that. Then we'll take a look at a very basic overview of HFC, which has been in the past the predominant reason why cable TV companies have been using fiber optic cabling. But then we'll also finish up by talking about some of the new generation of fiber networks that are coming out. You hear a lot of these buzzwords and acronyms like FTTH, fiber to the home, PON, RFUG, WDMs, things like that. We'll try and sift through that alphabet soup and get you to a point where you're able to, when somebody starts talking about some of those terminologies, you'll know what they're speaking about. So let's go ahead and kick off the presentation today by talking about how a basic fiber optic system works from a 10,000 foot view. And in a fiber optic network, essentially what we're going to be doing is we're going to be taking an electrical signal and we are going to be converting that to an optical pulse using a transmitter. And this transmitter can be either an LED, which is essentially a high-powered light bulb, or it can be a laser depending on the application. And today we are going to be talking about long haul, things like HFC, fiber to the home, and in all of these applications the transmitter that we're going to be using is going to be a laser. While it can be an LED, everything when we go forward talking about transmitters today, we're going to be referring to some type of laser that's going to be used to put an optical pulse onto a piece of fiber optic cable. So we're going to take that electrical signal, we're going to convert that to an optical pulse, and we're going to send that optical pulse down a piece of fiber, which is represented by the yellow line here. So that's going to be my base piece of optical glass that's going to be carrying that optical pulse over to the receiver, and that receiver is going to interpret that optical signal and convert it back to an electrical signal that I can use at the far end. So essentially what we're doing is we're doing an opto to electrical conversion and then converting that back on the other side. And one of the important things about a fiber optic network is that we need to make sure that the receiver receives that optical signal with enough power so that it can intelligently interpret that signal. If that optical signal gets attenuated or there's too much loss along that pathway, we're going to have issues at the far end and we're not going to be able to detect what that optical signal is trying to say. So a lot of the main things we're going to be talking about today is keeping that fiber optic link intact by handling fibers properly and things of that nature. So in most fiber optic networks, we are going to be using 2 fibers, but we'll talk about a couple of other applications later in the presentation that may only use 1. But in most legacy fiber optic networks, we will have 2 fibers, and one will be transmitting, in this case, from the left side of the screen to the right side of the screen, and we will flip that around using a secondary fiber so that we have bidirectional communication. Also wanted to mention, if you do have any questions, go ahead and type them in and we will try to get to those at the end of the presentation. So if I go over something or you'd like me to cover something in a little bit more depth, just go ahead and let me know. So one of the things a lot of people ask me when they learn that I work with fiber that don't work in our industry, they say, why would you use fiber optic cable versus some other type of cable that's already in the ground or being installed? And there's several reasons for this, and one of them is that compared to a copper twisted pair cable or a coaxial cable, the amount of bandwidth capacity is a lot higher compared to other types of traditional cabling. So we're going to be able to have a lot more throughput if we use a fiber optic cable. That's one major advantage that we're starting to see people use fiber for. And another reason is that an optical signal can travel further before it needs to be regenerated. So instead of having to put a lot of amplifiers and other things like that, actives out in the field, a fiber optic signal can travel further than a conventional electrical signal can in most cases. And another major advantage is that it does not have any type of sensitivity to any type of interference from electrical fields. So since we're using light instead of electricity to conduct our signal, we can put this right next to some type of power source. We're going to be immune to any type of interference. So those are some major advantages. Another advantage that people use fiber for is that it's very small. So compared to a large bundle of copper cables like you see here or some of the larger coax cables that are used out there in the field, we can put 144 fibers in a jacket size that's about 1 inch. So essentially it's going to be able to be much smaller and lighter. A couple of the challenges associated with fiber is that it is typically a little bit more expensive to put in, right? You have to pay for a fusion splicer to go out and splice your fiber, and it can be a little bit more expensive on the upfront end, but we're really starting to see a lot more fiber being deployed for the reasons that I mentioned earlier. And if we take a look at all the different applications for fiber optic cabling, it's really grown over the years. It began as a long-haul telecommunications type product, so in other words, for long-distance calling between Chicago and San Francisco. But we started to see, many years ago, cable TV companies started to take a look at the advantages of fiber optic cabling, and they decided they wanted to leverage that and came up with hybrid fiber coax that we'll talk about a little bit later, which is a technology that's used for your, obviously for your cable TV applications. But then we started to see a lot of the older telephone companies who were planning on repairing or replacing a lot of their copper cabling that was out in the field. They decided to start doing fiber to the home that we'll talk about in a little bit. And we're also starting to see some cable TV companies take a look at using a fiber to the home technology that brings a fiber optic cable all the way to the side of your home instead of terminating at a node. And we're also starting to see quite a bit of fiber being used for other applications like wind farms. If you're driving along and you see all those large wind turbines, in most cases, those are going to be controlled and monitored by a fiber optic cable because of one of the advantages that we talked about earlier. The distance limitations of copper would make it hard to reach all of those different towers. So they're using fiber optic cabling for that. We're also starting to see the Department of Transportation is starting to use cameras for a lot of their monitoring of the streets and the roadways, and many of those cameras are being fiber fed. And we're also starting to see a lot more cell backhaul, and essentially what that means is that instead of using some type of copper or traditional cabling to feed those cell towers, we're starting to see a fiber optic cable being used because it has a lot more bandwidth capability. And lastly, one of the other major reasons that MSOs are using fiber is to provide business class services to customers. So for example, Clearfield, we have a fiber optic cable link coming into our business where we're getting high-speed internet. That's another way that you can use fiber optic cabling, is to provide those high-speed business class networks. So now that we understand how fiber can be used, let's take a look at the actual mechanics of how an optical signal passes through a piece of glass. And so what we're seeing here is an illustration of what's called total internal reflection. And what that means is that in a piece of fiber optic glass, when it's being manufactured, what they do is they take a piece of very, very pure silica glass, and they take that and they make it into a strand, and then they put a different material or a cladding type of material around that tube of glass. And what happens is that the tube of glass, or the core that's in the middle, has a higher index of refraction or different characteristics than the cladding. So what happens is where the optical signal is inserted onto that glass, at the barrier between the core and the cladding, if I hit that, the barrier between those two materials at an angle shown as like the blue line that we see right there, if we hit that at the correct angle, 100% of the optical signal is going to be reflected back through that core and down the piece of glass. So essentially what we're doing is we're creating a tubular mirror that we're going to be using to reflect a piece of, or reflect the optical signal back and forth through that glass. And you can see the illustration there of the green laser being bounced back and forth through that glass. And that's an important concept, is that we want to always make sure that when that optical signal is passing through that glass, that we don't create any type of issues where we're going to violate that critical angle. And that's shown as the red lines there. If I ever was to bend this fiber at too great an angle. Now instead of having that optical signal bounce back and forth through the core of that glass, we're going to have light escaping out into the core, escaping out of the core and into the cladding. So essentially it's a neat way of being able to have light, which normally propagates in a straight line. We can now have light go around corners, we can make bends with it, as long as we're not violating that critical angle. And what we're looking at here is a representation of where fiber optic light falls in the electromagnetic spectrum. So what we're looking at here is all the different types of electromagnetic energy that exist in the world today. And as you can see, I've highlighted a small section of this, and fiber optics uses a small section of this spectrum in the infrared part of the electromagnetic spectrum, and we'll blow that up here in just a moment and let you take a closer look at that. But just keep in mind that when we are talking about optical signals on a piece of glass, it's not going to be visible to the human eye. So we always want to make sure that when we're handling fiber optic cabling and equipment, that we want to make sure that we're never going to be exposing our eyes to a situation where we may have those beams going into our eyes, because even though we can't see that light, there may be something on that glass, an optical signal, that we can't see that can damage your eyes. So you always want to be very, very careful of that when you're working with fiber. So what we've done here is we have taken that part of the electromagnetic spectrum that we're going to use for fiber optic glass, and that's going to be approximately from 800 nanometers up to 1675 nanometers. And essentially what we're going to be doing here is we're going to be looking at the different bands or colors. I say that they're colors, but they're not actually visible colors to the human eye, but it's a useful analogy for us to be able to use, that these I will refer to colors, but essentially what I'm talking about is the different wavelengths or usable wavelengths that we use in fiber optic cabling. And you'll notice that from about the 1200 to 1700 nanometer section that we're looking at in this illustration, we're looking at the usable wavelengths that we can use for fiber optic signals. And you'll notice that there's two bands that I've circled there, and those are going to be the O band and the C band. And those are going to be two very popular wavelengths or colors that we're going to use in fiber optic technology. And the reason for that is you can see that the dashed line that I've introduced onto this chart shows the attenuation or the amount of loss per kilometer that each one of those different wavelengths is going to attenuate. So as you can see, at about the 1310 or 1300 nanometer section and the 1550 nanometer section, that line is pretty low. So what that means is that optical color or that optical signal is going to attenuate at a lower rate than some of the other colors that we can use. So you'll see a lot of different electronics. They will call out either a 1310 nanometer or a 1550 transmitter. What they're referring to is the wavelength that we're going to be inserting onto that glass. And the reason why those two have been selected is that those optical signals are going to be able to travel farther before they need to be regenerated. And you'll notice that there's a section of that dashed line that's been highlighted. And what that is what we call the water peak. And in older styles of glass, or water ions would be captured inside of the core of the glass, and that would cause a high attenuation rate at that particular section of the single mode spectrum. So it made it unusable for certain applications. You'll hear a lot about different types of glass called zero water peak or low water peak glass. And what that is that's a new type of glass that has eliminated that water peak or that bump in the attenuation line that we see there. So instead of having that large increase, it's more of a flattened line so that you can use that for additional services. And in typical situations where people are using legacy type networks, what people are doing is they're typically only using one of these bands, so the O band or the C band, and they're only putting one type of service onto a single piece of glass. But you can see the green and the yellow and the other colors, the L bands and things like that, those are actually available for use by other services. And we'll talk about that later on, but just be aware that by putting different colors onto the same piece of glass, we can have multiple services on a single fiber, which is called wave division multiplexing. And we'll talk about that in a little while. Transmitters and receivers, we talked about this a little bit earlier. One of the reasons why we're going to be using a laser versus an LED is that it has a much higher bandwidth capacity, and it also can travel a lot farther distances before it needs to be regenerated versus LEDs. And LEDs are typically going to be used in what's called a multi-mode fiber application. And the two types of major fiber that's used in the industry right now is going to be either multi-mode fiber or single-mode fiber. And the difference between them is that typically multi-mode fiber is going to be used for much shorter distances. Typically you're going to see these inside of a building or in a local area network being used as a trunk cable inside of a single facility. It's not ideal for long distances, and it's also used in lower speed applications. Just be aware there is two different types of glass out there. One of them is called multi-mode, and usually the main way of telling if it's a multi-mode cable is that the jacket on the cable, as you see here, is either going to be an orange color or it's going to be an aqua color. And the multi-mode cable uses a much larger core. Remember we talked about the core and the cladding? The multi-mode cabling is going to use a large core of glass. It's typically going to be between 50 and 62.5 micron, depending on the application. So because of that, it is not compatible with single-mode glass that we'll talk about here in just a moment. Single mode glass is going to be the type of fiber that we are going to be talking about for the rest of the presentation. The only reason I really mentioned multi-mode cabling is that in case you ever run into it out in the field and somebody says, hey, can you plug this single mode cable that you're bringing in from the outside world, can you plug it into my multi-mode network? It will not work. Typically you're going to have a core mismatch because the core on the glass on the single mode fiber is only going to be about 9 microns across compared to the 62.5 or 50 micron glass that we have, and that'll cause major issues. And the reason why we use single mode glass for most of our cable TV and telecommunications applications is that it can go much farther distances and you can run a lot higher speeds on single mode glass. And as you can see here, there's a major difference in the construction of the single mode glass versus the multi-mode glass that we looked at before. And we are going to be looking at the core is only 9 microns across versus the 62.5. This makes it a situation where whenever we have fiber optic connectors, typically you're going to see that the type of equipment you're going to be using for single mode is more expensive because the tolerances when we manufacture a patch cord or jumper or piece of equipment that works on single mode fiber, we have to be much more precise because that core is a lot smaller and it needs to be polished more precisely and tested more precisely. Those of us that have not worked with fiber a lot in the outside plant world probably don't know this, but the fiber optic color code works on a basis of 12. So in other words, if you're looking at most outside plant cables that you see running down the road or being buried, typically those are going to be sold in multiples of 12. And the reason for that is that they typically use multiple buffer tubes, and inside each one of those buffer tubes inside the cabling is going to be 12 different colored fibers. And the color code goes blue, orange, green, brown, slate, white, red, black, yellow, violet, rose, aqua. And the reason why they pick 12 different colors is that the human eye can easily differentiate between 12 different colors. If you start getting above that, it's going to be hard for you to tell the difference between 3 different colors of blue versus only just blue and aqua. So that's one of the reasons why we have 12 fibers in an individual jacket. So when you look at for example, a 144 fiber cable, you will have 12 different buffer tubes inside of that 144 fiber cable. And then each one of those individual buffer tubes will have 12 different colored fibers inside of it. And the major two types of cabling that is installed typically in the outside plant world is going to be what's called stranded or loose tube fiber, as shown on the left, where each individual fiber is a strand. But we're also starting to see a lot more ribbon fiber being introduced into the outside plant network. And essentially, ribbon fiber is going to be the exact same fibers that you see in a stranded application, except they have been taped or there's a matrix on them so that it is formed into a ribbon. And the main reason why people are using ribbon fiber versus a stranded type of fiber is that it's much easier for mass restoration because you can fusion splice 12 fibers at a time. Instead of having to go out and if, say, for example, a fiber optic cable gets damaged for one reason or another, if you have stranded fiber, you would have to go out and individually splice 144 fibers. Whereas with ribbon fiber, you can go out and use a mass fusion splicer and splice all 12. A couple of the downsides of working with ribbon fiber is that in some cases it can be difficult to access individual fibers inside of that matrix. And also with ribbon fiber, it requires a more expensive splicing machine. So instead of having just a single fiber being spliced at a time, it has to align all 12 and fuse 12 at a time. So there's benefits to both types of solutions, but most of the time when I'm dealing with the MSO cable TV companies, we're looking at stranded fiber, but you may see ribbon fiber becoming a little more popular as years go by and fiber counts increase. The type of electronics that puts an optical signal onto a piece of glass is called a transceiver. And in most cases, transceivers use a two-port system where there's going to be two fibers coming into this device. One would be a transmit, and the other one would be a receive port. As we mentioned earlier, you'll be using one fiber for your downstream and another for your a separate one for your upstream traffic. And again, just keep in mind these are called transceivers because they do transmit and receive. And these can be plugged into various electronics like nodes or routers, things of that nature. And one of the interesting things about transceivers is that they used to come in just varieties of either the 1310 or the 1550 nanometer that we talked about previously. But we are starting to see different optics being available with different colors so that we can multiplex those onto single fibers, things of that nature. And you can get these transceivers in different power levels so that if you're going a farther distance, it would have a higher dBm or higher transmit power so that you can go farther distances. Now that we understand a little bit about the basic components that are used in a fiber network, let's take a look at what happens to that optical signal as it travels down that piece of glass. And there's a couple of things, a couple of attenuation things that happen to that optical signal as it passes down a piece of glass that we can't do anything about. They're inherent to fiber optic technology, and those are absorption and scattering. But there is one method of attenuating fiber that we can avoid, and those are going to be called microbends and macrobends. And we're going to try and keep our optical signal as strong as possible because we want it to travel down that glass as far as we can. So as to absorption and scattering that we'll talk about here, we can't avoid those, but we can avoid problems from microbends and macrobends, and we'll discuss that in depth later when we talk about handling of fiber optic cabling. So absorption is going to be one way that the optical signal is going to be attenuated as it travels down that piece of glass. And what that means is that as that optical signal is reflected through the core of the glass, it's going to encounter small impurities in the glass. And as it encounters those impurities, it's going to take that optical signal and convert that energy over to heat, which means that I'm going to lose a small amount of my optical signal. So again, absorption we really can't do anything about. It's just be aware that that's one of the methods that your optical signal is going to lose some power as it travels down the glass pathway. And another thing that happens to the optical signal as it travels down that core is that it's going to encounter different particles inside of that glass, and some of that optical signal is going to reflect, instead of through the total internal reflection, it's going to reflect out into the cladding. So we call that scattering, and again, there's nothing really we can do about it, but just be aware that that's what happens. And there is a certain type of scattering called backscattering, which means that as that light encounters those particles, it's going to reflect some of that light back towards the transmitter. And we're going to use that backscatter later on when we talk about testing of fiber, but just be aware that that backscattering can be used by a device called an OTDR to measure distance and different events that are happening inside of that glass. So absorption and scattering, we know we can't do anything about those two things that are going to attenuate our optical signal, but there are two things that we can try and avoid so that that optical signal stays as strong as possible. And one of the things that we can avoid is what's called a macro bend. And you can see that's shown on the right-hand side of the slide here. And what that means is if you were to take a fiber jumper or a cable and bend that over a piece of sheet metal or make too tight of a bend, instead of having that nice, easy, reflecting pathway as we go down the core of the glass, we're going to violate that critical angle, and now all of a sudden some of our optical loss is going to create an issue later on in the network. So we want to try and avoid any type of sharp edges whenever we're running a fiber jumper or a cable, because now we can possibly have loss of service if we have a tight bend in that fiber. Also, one of the other things that we encounter sometimes that can be a problem and create excessive loss in a piece of glass is what's called a microbend. And a microbend is when someone, for example, was to take a bunch of fiber cables and zip tie them together very tightly. That can create a dent in that glass. And again, the same thing is going to happen. Instead of having that nice reflective pathway, now we have a source of problem, because now we're going to be reflecting some of that optical light and it's going to escape. So the two main things we want to do is when we're handling fiber, we want to make sure we're not zip tying them real tightly. It's typically better to use some type of a loose Velcro strap to be able to keep your jumpers bundled together. Zip ties are pretty much fiber optic cable. It's one of our worst enemies that we encounter. A lot of times people call us up and say they have a problem with their fiber, and we come out and we clip off the zip tie, and all of a sudden the problem goes away. Obviously was caused by that zip tie. Let's take a look next at what's called an optical link or a power budget. And what we're going to be talking about on the next 6 or 7 slides is going to be where we calculate how much optical loss we're going to have along our pathway. As we mentioned before, we want to understand what the sensitivity of our receiver is and the power level of our transmitter. And we're going to need to make sure that whatever physical link or fiber pathway we construct, we don't introduce too many objects or events into that piece of fiber where we create too much loss and the receiver is not able to receive that power. So over the next couple of slides, we're going to take a look at how we calculate how much optical loss we're going to have along that link, and we're going to take a look at in-depth each one of those types of events, and then we'll take a look at a calculation that adds up all those different events in my optical pathway. And one of the main things in our network that is going to introduce some loss, or what we call insertion loss, in our fiber optic pathway is the use of connectors and patch cords. And typically these are going to be used in areas such as patch panels, where we terminate our outside plant fiber into a head end, for example. We're going to need to terminate all those outside plant cables into a patch field, and then we're going to need to run a jumper from our electronics to that patch field. So anytime we introduce a mated pair of connectors, we are going to have some loss. And typically when you see a yellow patch cord like the one you see here used in your head ends, they're going to come with a birth certificate or a value of the insertion loss on each one of those connectors. Typically manufacturers like Clearfield will provide that and say that when it left the factory, we tested it, this patch cord will give you X amount of insertion loss if used in your network and mated to another quality connector. And typically you're going to see the insertion loss value out in the industry is about 0.3 dB insertion loss. So we want to make sure that we're counting up those connector pairs as we go down our fiber optic link. We also want to make sure that we are doing proper cleaning and inspection of those before we plug them in, because if we have dirt and dust and contamination on the end face of those fibers, now instead of being 0.3 in insertion loss, it can be much higher than that. Remember, that core is only about 9 microns across, and even a tiny speck of dirt or dust or contamination can create a loss event that we really don't want to have happen. And this is essentially going to be a close-up of all the different types of fiber optic connectors that are used out in the industry right now. And as you can see, they have two major differences. Some of them have a blue boot and connector body, and some of them have a green connector body. And we'll talk about the differences between those here in just a moment. But just be aware that those two types of connectors, you'll never want to mate a blue connector to a green connector, and we'll talk about that in just a moment. But be aware that the blue connectors have a flat end face when they're mated, and the green have an angle or an 8-degree angle on the end face. So when you mate those up, they you definitely would want to have a mismatch if you mated up two different types of patch cords. So the APC stands for angle polished connector, and the UPC stands for ultra polish or flat polished connector. Each one of those connectors shown on the left is typically going to mate a single fiber inside of each one of the connectors, but there is a new type of connector that you may see out in the field as well in the bottom right-hand corner called an MPO or an MTP connector. And those connectors, instead of mating just a single fiber at a time, Clearfield, we can manufacture a patch cord that can mate up to 24 fibers at a time. So essentially, people like to think of it as sort of a ribbon connector. So in other words, instead of just mating a single fiber at a time, it mates many, many fibers at a single junction point. And you may also run into a connector shown in the upper right-hand corner called an HFOC, or hardened fiber optic connector, and those are typically going to be used in an outside plant fiber to the home type application, and it has a ruggedized sealed housing around it that plugs into a terminal that is also environmentally sealed. So this is a close-up that shows the difference between the UPC, or the ultra polish, shown on the left, and the APC style of connectors, which is shown on the right. And the reason why the green connector is typically picked by most MSO companies is that 8-degree angle, what that does is it reduces the amount of light that is reflected back towards the transmitter. The UPC connectors act as a mirror and reflect some of that optical power back towards the transmitter and can create ghosting effects and other types of issues and errors in RF cable TV type applications. Whereas with the 8-degree angle, instead of reflecting that optical signal directly back towards the transmitter, it reflects it away from the transmitter and reduces your back reflection. And as you can see here, this is an illustration of an angle polished connector mating up with an angle polished connector. That's going to show you that you have a good physical connection there and those fibers are going to mate correctly. And also a UPC to UPC connector, flat polish to flat polish is going to work well. But an issue, as shown in the bottom, would be if we ever tried to mate up an angle polished and an ultra polished connector. We're going to have an air gap there, and that's going to create a high level of attenuation out in the field. So if you ever see a patch panel port that's blue, don't plug a green patch cord into it and vice versa, because you'll have a huge problem. It can create many dB of loss and create a big issue in your network. Besides connectors, we're also going to want to calculate how many splices we have out in our network. And depending on what the specification is for whatever your project is, the splice loss is typically going to be between 0.02 and 0.05 dB. So you can see that's a lot less than a physical connector that we were talking about earlier, because we're going to be fusing those two pieces of glass together. It's a much lower loss connector, but we also want to make sure that we are calculating that, because if we have a lot of splices in our network, that's going to add up over time. We're also going to want to calculate the distance that we're going to be traveling, because as we talked about before, those optical signals are going to attenuate over distance. And you'll notice that if we were to put a 13 nanometer wavelength onto that particular piece of glass, we're going to want to calculate that out at 0.33 to 0.35 dB per kilometer. So as those kilometers add up, we're going to want to make sure that we're calculating the optical loss as it travels down the piece of glass. And you'll notice here that the 1550 nanometer that we talked about earlier, which is typically what most cable TV companies are using as their wavelength for their light, is going to be 0.19. So that's considerably less than the 1310 nanometer, which means it's going to be able to travel further before it needs to be regenerated. Another thing that can create optical loss in our fiber network, especially if we're doing fiber to the home, is going to be what's called an optical passive splitter out in the network. And essentially those are going to be used for fiber distribution, where we're going to take a single fiber in and we're going to split that out to a certain number of users. And as you can see here, the insertion loss is going to be documented typically with the spec sheet that you would receive from your manufacturer. But as you increase those splits, your insertion loss is going to go up dramatically. You can see a 1x32 splitter that is a typical fiber to the the home type application is going to have about 17.6 dB of insertion loss as it passes through there. So this is going to be a major contributor to your loss if you're doing a fiber to the home network. It just needs to be calculated properly. Also, devices such as muxes and demuxes that we'll highlight here in just a moment in a CWDM or wave division multiplexing network can also create insertion loss. And again, that should be provided on a spec sheet from your manufacturer that would tell you if, for example, you were going to be combining 4 different colors or 4 different channels onto a single piece of glass, that multiplexer or that combiner is going to be a source of optical loss that you're going to want to calculate and make sure you keep that in mind. So if we're going to try and go ahead and figure out how much optical loss we have between our transmitter and our receiver, we're going to want to calculate the number of connectors we have, and then we're going to take a look at our spec sheet from our manufacturer and make sure we understand exactly how much insertion loss is going to occur per mated pair. Then we're going to take a look at how many optical splices that we had to put out in the field to be able to have our fiber optic link be connected. Then we're going to take a look at how far did that optical signal have to travel in kilometers and calculate that out as well. Lastly, we want to take a look at any type of optical components that we're going to be introducing, such as optical splitters or multiplexers, and add that up. And typically what most people do is they will put a certain amount of margin, around 3 dB, of essentially basically it's going to be a slop in case you have any type of issues that come up later on. You want to make sure you're not at the very, very end of your link budget, because if all of a sudden you have to put a couple splices into your network later on due to network damage, you don't want to be right at the end of that link budget, and now since you introduce a couple of splices, now you're not able to make a good connection. So here's an example of a real-world link budget. If, for example, we were going to be having a 23-kilometer 1550 network, and we were going to have a SC angle polished connectors, 4 splices, and 2 CWDMs, what we would be looking at is we'd be looking at 1.2 dB of insertion loss from our connectors, only about 0.08 from our splices, and based on my length loss, I would have 5 dB of insertion loss because I'm going to be going 23 kilometers. And then if I introduce any type of a CWDM or optic device in there, I'm going to create 6 dB of loss, and then I'm going to add in my 3 dB of margin. So in this particular application, I would expect to see around 16 dB of insertion loss, and we would want to make sure that when we're sourcing our transmitters, transceivers, that we have enough optical power to overcome that amount of loss. So once we've done that calculation and we've gone out and physically constructed that fiber link, we're going to go out and test and make sure that that link is fully functional. And there's 2 main tools that people use for testing a fiber optic cable. And the most common that you're going to see is going to be a light source and power meter. And these tools, you basically need to be at both sides of your fiber optic link to make this work. And what you do is you put a known amount of power on the far side of that fiber optic link. And then on the other side, you're going to go over and put the meter on there and see how much comes out the other side. So it's a very basic way of telling how much insertion loss occurs in your network. And say, for example, we did our link loss calculations and we figured that we were going to have about 16 dB of loss. Say that we go out and we do a test and there is an excessive amount of loss on there. Say it's 22 dB of loss. This machine would tell us that we have that amount of loss, but it would not tell me where in the network that problem is occurring. And that's where we would use an OTDR. And an OTDR is the device that measures the backscatter of the optical signal. So what it does is it puts a pulse onto that optical fiber and it measures the backscatter. And what that does is it tells us the magnitude of the loss events and where they are in the network. So if, for example, I knew where each one of those events is supposed to be, and I'm able to map it out, I can figure out, okay, I've got a splice case that's 4 kilometers out in my network. This machine would say your event is out at 4 kilometers and it's X amount of insertion loss. So it'll provide you with a map like the one that you see here that tells you the magnitude of each event and also, more importantly, where it is in your network. So what most folks do is after they construct a fiber optic link, they will measure each one of their fibers with an OTDR and record those results. And then if there's ever an outage, they can go back to those original results, and they can now do a retest and find out what the difference is between those two so that they can analyze where the new problem occurs. So let's take a look next at proper fiber management techniques. And one of the things that Clearfield really tries to make sure that people understand is that we want to make sure that when we're handling fiber optic cabling and fiber optic jumpers, that we're making sure that we're working with a couple of key concepts. And one of them is bend radius. And what bend radius means is it means the smallest circle that you can wrap a piece of fiber optic glass around before it starts to attenuate. And you can see here that typical single mode glass that you're going to see out in the industry right now, such as the standard 652 type fiber that's used out in the industry right now, you can wrap that around a 1.5-inch bend radius or a 3-inch circle, and you won't have any type of excessive attenuation. But if you start to wrap that around a smaller circle, or you start to coil that up too tightly, we can have excessive loss based on the internal reflection that we talked about earlier. And you can see that the device I've shown in the bottom right-hand corner is what's called a visual fault locator. And these can be used for finding areas of microbends and macrobends. What it does is essentially, instead of using infrared light, it puts an actual physical red light, visible light onto that fiber. And you can see where the light is escaping out into the clad. And you can see that little circled area there is an area that shows where I have a damaged fiber. But it could also be used to show you where you have any type of microbends or macrobends. And sometimes if you were able to release those fibers or get them away from a tight bend, that red light will go away and your problem may be solved. Besides the standard type of glass that's available out in the industry, there is some new type of glass that's being developed called bend-insensitive glass. And bend-insensitive glass, if we're to look at it from a very high-level overview, there's two main types of bend-insensitive glass out there. There's the G657A and B. And essentially the difference between those two is that the G657A type of glass can be wrapped around basically the diameter of a quarter or a coin. So you're able to wrap that much tighter than you can without experiencing the same loss. So we're starting to see people put bend-insensitive jumper cables in areas where they may be exposed to some type of excessive bending and things of that nature. But the nice thing about the G657A fiber is that it's backwards compatible with other types of standard glass that's available out in the industry. And there's also a new type of bend-insensitive glass called G657B, which is not completely backwards compatible with standard types of glass, but you can wrap it around a pencil before it starts to attenuate. So again, you're able to get a much tighter bend radius, but haven't seen a whole lot of the B version, but we do have many customers that purchase the bend-insensitive glass. And I always tell people that you want to make sure that you're treating that bend-insensitive glass as if it was standard glass, but just use that as a fail-safe in case there is ever an issue. You are protected a little bit more using the bend-insensitive jumpers. And one of the things that we're going to want to keep in mind is pileup of jumpers in a head-end type environment. And if those of you who spend time in your head ends, many times you'll see that those fiber jumpers are stacked several inches deep in the overhead troughing or in horizontal troughs inside the frame. But there's a group that comes up with fiber optic termination and management, and they're called Telcordia. And they suggest that you should never have more than 2 inches of pileup in any particular area. Because if we start to have some type of a kink in our fiber and then we start to stack those jumpers on top of each other, we can have excessive bending and excessive issues going on. And one of the ways to avoid that problem is to use smaller outside diameter jumper cables. And as you can see here, most of the standard jumpers that have been used in the past have a 3 millimeter outside diameter. And if we actually migrate to the smaller 2 millimeter outside diameter jumpers, we can more than double the amount of jumpers we put into a small area. And again, this is going to be the situation, this type of product, it would be a horizontal trough that you would see for running jumpers. And by simply switching to 2 mm jumpers, I can go to 1,020 jumpers in that small area versus only 440 of the 3 mm jumpers. Excuse me, I jumped ahead there. Some of the things that we're going to want to take a look at when we're handling fiber are going to be what we call the fiber management basics, and we'll take a look at those here in just a moment. One of the things that we want to make sure of is that when we're working with fiber that we have access to each one of the individual jumpers. So when we walk up to a patch panel, we want to be able to easily remove each one of those fiber connectors and not accidentally unplug one of the other ones next to it. Most of the connectors that you're going to see right now in cable TV networks are going to be the Sam Charlie APC connector, but there is a smaller connector called the LC, which is half the size of the Sam Charlie connector that's shown here. And while it does improve the density that you have in your network, you can basically double the amount of fibers in that particular panel or shelf. One of the problems with the LC connector is that it's somewhat like the RJ45 connectors that we're familiar with. It basically has a trigger, and if you accidentally reach in and unplug the wrong jumper, that can be a big, huge issue. So access, you always have to be able to get at the fibers and be able to individually remove each one of those. Access is really important as well because we want to be able to easily do inspection on the end faces of our fiber. And one of the things, if you're working in a head end, that you should always have if you're installing fiber is an end face inspection scope like the one that you see here. And essentially it's just a microscope with a screen on it so that you can magnify the end face of that piece of fiber. And as you can see here, this is going to be an extremely dirty end face shown on the left under a scope, and on the right would be a properly cleaned type connector that you would want to mate into a patch panel. And if you don't do proper cleaning on an end face before you plug it into a patch panel or a piece of gear, you can be transferring that contamination from one connector to another. So you always want to make sure that you're cleaning both the connector that you're plugging into in a patch panel as well as the patch cord that is coming from the manufacturer. You'll also want to take a look at the end face quality before you plug in a connector. And on the left, we can see an end face that has an excessive amount of epoxy left on it from the manufacturing process. And you can also see there's a lot of scratches and impurities on that glass as well as the ceramic ferrule. So what you'd want to do is you'd want to discard that damaged cable or send it back to your manufacturer. But as you can see on the right-hand side, that would be a patch cord that would be properly polished and terminated so that that would be able to be installed into your network. As we talked about before, bend radius protection is one of the things that you're going to want to practice and have in your fiber management technique. And we never are going to have exactly the right length jumper cable. Typically we have an excess 2 or 3 feet of cable that we're going to need to manage between our patch panels or between our electronics and our field side panels. And whenever we do that, we want to make sure that we have at least a 3-inch spool that we are going over so that we don't violate that bend radius. And we're also going to want to make sure that we have enough space for all of those jumpers. We don't want to be cramming them into a small area. And as you can see here, these are what's called inter-bay cable management panels, and they take up about 5 inches of space in a head-end type environment. But they're excellent for taking up fiber. Instead of just sticking them into some type of a little troughing system with zip ties or whatnot, this is really going to help overcome any type of bends that you're going to have that would bring your network down. And physical fiber protection is also important. The covers that you see on your patch panels, I walk into head ends sometimes and I'll see all those plastic covers over in a corner because people don't want to put them back on. But that's a pet peeve of mine because if somebody walks by a patch panel with a tool belt and snags one of those jumpers, that can be a huge problem. And those covers are excellent for keeping those fiber jumpers routed properly and away from areas where they could possibly be damaged. Route diversity is also going to be important. As you can see here in this particular illustration, the fiber jumpers in these types of panels, half of the jumpers are going to be routed to the left and half of them are going to be routed over to the right. And the reason for that is so that we don't create a congested pathway and don't keep routing jumpers the same pathway every time. So if you want to make sure that you understand from your manufacturer how those jumpers are supposed to be routed so that you're not creating excessive pileup and congestion. And one of the other things we touched on previously was density. We want to make sure that our fiber management, we want to make sure that we're not packing too many connectors into a small area. Because if we do that, it might be hard for a technician, especially techs with bigger hands, to be able to get in there and work. So you'll hear a lot of people saying, I want as many fiber connections as I can in a small space. While that is nice from a space-saving standpoint, it has to be usable by the technician as well. And lastly, and almost most importantly, one of the major things that we're going to want to do when we're working with fiber is we're going to identify each fiber in a patch panel port. And by that, I mean that we want to know which one of those fibers is routing to which piece of equipment, and also which one of those fibers is being connected to what outside plant fiber. So the reason why we want to make sure that we understand the fiber identification is so that we don't accidentally turn down the wrong service. You can imagine how disastrous it would be if you were trying to do service on a particular fiber and you thought you were pulling down a node during a service outage, but you actually pulled down a hospital, right, that's on a business class circuit. You always want to be able to easily walk up to a patch panel and see a designation card like the one shown here and be able to easily identify which port is connected to which outside plant fiber and also what it's connected to inside your head end. And most people will also put some type of a flag label on the individual fiber jumper as well as managing each one of the ports as well with a designation card. So just to recap what we want to do when we're handling fibers, we want to make sure that we're being cognizant of our bend radius and making sure we're protecting that. Make sure that we keep all of our connectors clean and inspect them before we plug them in, and make sure that we have an easy way to identify all of the fibers in our head end. And especially with a lot of the new technologies that are coming out, there's more and more fiber being installed into our head ends, and we want to make sure we're able to easily identify each one of those fibers. So I've got about 5 more minutes here. I've gone a little bit long. Hopefully that'll be okay if I go maybe 5 minutes long. We've got about another 10 minutes of the presentation. But what I wanted to cover is some of the current and future applications for fiber as they apply to cable TVs and MSOs. Let's start off by talking about HFC, or hybrid fiber coax. Essentially, hybrid fiber coax is going to be the main way that cable TVs are using fiber optic cable right now. And simply what that means is that we're going to use a fiber optic cable to connect to nodes out in the field, and that node is going to take that optical signal and it's going to convert it over to an electrical signal. And from that node out, it's going to be transmitted electrically over a coaxial cable and then amplified typically from there. So the reason why we are going to use fiber and coax together, that's why it's a hybrid network, is because we're using fiber and coax together, is that we're able to go farther distances and have higher bandwidth from my head end or my hub out to the node. That's going to be the major advantage with an HFC network. And typically you're going to see most nodes, a lot of the older nodes that you see out there are going to be fed with 2 fibers. One would be your forward fiber and the other one would be used for your return. And those 2 fibers would come in through a service node cable, and that's usually going to be some type of a stub that has a metal fixture on it that would be screwed into the node case and would be terminated with typically SC connectors, and those would plug into the electronics inside of the node. And from the node towards the home, that would obviously be a coaxial cable of some type or another. And since you folks probably know more about HFC than I do, I'm not going to spend a whole lot of time on that, but I figured I would go ahead and start talking about some of the new buzzwords that are out in the industry right now. You've probably heard the term PON or RFOG thrown about, as well as active Ethernet and WDM networks, and we'll spend a minute or two on each one of those technologies and let you kind of see what those are all about as far as they apply. So what you've probably heard the word PON or GPON technology thrown about, and essentially what a PON stands for is passive optical networking. And by that, I mean that there are not going to be any active electronics or nodes out in the field. It's going to be a purely passive network all the way from the head end to the side of the customer's home. And there's several different types of PON out there. One that's typically used in the telephone network is called GPON, or gigabit capable PON. And what that is that provides a 2.5 gig downstream and a 1.25 gig upstream pathway that's shared on a single fiber. And we are going to create a fiber called a feeder fiber that's going to originate at our head end, and that's going to contain all of the optical signals for however many users I want to have on that particular fiber. And when that feeder fiber goes out into the network, we are going to optically split that and send each one of the output legs to a particular customer. So that could be, for example, a 1x32 splitter. And that 1x32 splitter, each one of the outputs from that splitter is going to be routed to a home, where on the side of the house I'm going to place a device called an ONT, or an optical network terminal. And that's going to convert over to an electrical signal such as an RJ45 or an RJ11 style connector for telephone and Ethernet. So what's really interesting about this type of technology is that it's purely passive, and it's also pretty high bandwidth compared to a lot of the other applications out there. And what we're looking at here is going to be the optical network terminal that would be on the side of the home that would be used to convert the optical signal over to an electrical signal. And as you can see here, there is going to be one fiber coming in, and we have multiple copper interfaces coming out of that device. So that's basically what most people are doing, and when you hear the word PON, what that means is they're using a single feed fiber out into a neighborhood, and then they will optically split that to different homes depending on the application. And some of the advantages of a PON are going to be that there are no actives out in the field, it's very high bandwidth, and we also have lower maintenance costs. And the reason I say that is that the maintenance costs go down because there's less interference on this type of product, because we're using an optical signal instead of an electrical signal. So we don't have to go out and sweep for any type of interference. It's basically all going to be passive, and we don't have to worry about electrical interference anymore. And there is a type of PON that was designed specifically for cable TVs. And the way that this works is it's called RFOG, or RF over glass. And in an RF over glass application, we're going to use a 1550 nanometer for our downstream, and we're going to use 1610 nanometer for our upstream. So on a single fiber, we can communicate bidirectionally using different colors, and it's going to allow us to be able to keep our existing head-end equipment as well as the existing customer prem equipment in place. It essentially replaces the node with an optical splitter out in the field. And this is going to be the electronics that you would typically see out on the side of the home that we would be looking at, that would be converting that optical signal over to a signal that could be used inside the house. And there's different ways of providing splitters in a PON or an RFOG type architecture. And one of the main ways of doing this is to place a cabinet out in the field that would house many of these 1x32 optical splitters. In other words, we're going to have a patch panel inside of this cabinet that would be terminated to each one of the homes in this community. And anytime a customer wanted to get service, I would take one of the outputs from the 1x32 splitter and plug it into one of the patch panel ports, and that would provide connectivity through the splitter out to whichever home I want to light up. And this is going to be typically the way most GPON and RFOG type deployments are being installed. The cabinet that you see here is going to be essentially a 576 home type cabinet that would be able to serve, as I mentioned, up to 576 homes using 18 1x32 splitters out in the field. Oops, sorry here, I jumped ahead a little bit. Another way of placing splitters is we have some applications where people will run a fiber all the way from each home back to a head end where we will place a patch panel, and those optical splitters are going to be placed in the head end instead of out in a remote cabinet. Typically this isn't the way most people are doing it, based on the fact that you need to have a lot more fibers coming back towards your head end. Instead of just running the feeder fibers out to a neighborhood, I now have to run a dedicated fiber all the way out from my head end out to the individual customers. And we're also starting to see people place optical splitters in splice cases out in the field. In other words, they will hard splice those 1x32s or 1x16 splitters out in the field instead of placing a cabinet. This is going to dramatically reduce the amount of money that you need to spend, because you don't need to place that cabinet. But with a distributed type split, like you see here, using these components, which are hard spliced, you have less ability to test and less flexibility when it comes to moves, adds, and changes. The last type of fiber optic technology for fiber to the home that we'll talk about is going to be what's called active Ethernet fiber to the home. And this really doesn't come up that much with MSOs, but I figured I would cover it anyway. One of the interesting things about active Ethernet fiber to the home is that in this type of an application, you can see that the splitter bay in the middle is going to be a series of patch panels, and each one of those SC-UPC ports that you see in that patch panel is going to feed an individual customer out in the field. So for example, this is going to be 864 residential customers that are going to have an individual fiber port in the head end. And now I buy a series of fiber optic routers, and now each one of those fiber optic ports is going to get its own port on a router. And one of the advantages of this type of a solution is that since we're not passing through a 1x32 splitter, we can actually go quite a bit farther distances. And this is going to be something that you see out in the rural environments quite a bit, based on the fact that you have a lot larger footprint that you can cover, because now instead of having that 17 dB loss by passing through a splitter, I can simply home run a fiber straight from my router all the way to the home. And again, sorry I'm running a little bit late here. I kind of ran a little bit at the mouth here. But I've got a couple more slides here. One thing I wanted to cover that's coming out is called WDM technology. And essentially what WDM technology is, I touched on this earlier, is that instead of using just a single color or a single wavelength on a piece of glass, we are going to use multiple colors or multiple wavelengths on a piece of glass, so that now instead of having to only have one service on that piece of glass, I can put many on there. And WDMs are typically used to overcome the problem called fiber exhaust. And fiber exhaust is going to be a situation where, for example, we may only have 12 fibers running out to a certain part of town, and we wish we had 144 based on the fact that maybe we have some cell towers or some business class services that have popped up and we don't have enough fiber. So what we would like to do, based on all these increases in bandwidth, is that we don't want to have to put out new fiber, right? Because we want to be able to use our existing fiber more effectively. We don't want to have to spend expensive labor costs, splicing costs, and material costs. So what we want to do is we want to use our existing fibers more efficiently. And the way that these work is that we would source individual SFPs or transceivers, and each one of those is going to have a different color or wavelength associated with it. And we are going to combine all of those different colors or wavelengths at one particular location, and then we will break them out again at the other side. So essentially, we're able to create virtual glass. Instead of having to put new strands of fiber out, we simply put a MUX or a multiplexer on one side and a DMUX on the other. And again, this would be showing those SFPs or GBICs that you can use with individual colored optics and different ranges. And this is going to be an illustration of what the MUX units are. So each one of those LC ports that you see there would be associated with a different colored SFP. We would plug that in, and then each one of those different filters gets concatenated together so that by the time I'm done, all of those individual wavelengths or colors come out of a single common fiber. And these are the different types of packages that you'll see those MUXs and DMUXs come in. Typically you'll see those in your head end placed in some type of a chassis. And the two main types of WDM technology that are available are going to be what's called CWDM, or coarse wave division multiplexing, and DWDM, or dense wave. And the big difference between coarse wave and dense wave type technology is that coarse wave is typically going to take up that single mode spectrum and it's going to cut it up into 20 nanometer spaces. So in other words, I'm going to take all of that available spectrum, instead of putting just a 1310 or a 1550 signal on there, I'm going to put a bunch of different colors on there. And this allows us to be able to do up to 18 different colors or services on a single fiber. The other type of WDM technology that I alluded to earlier is the DWDM, or dense wave division multiplexing. And what that allows us to do is it allows us to put many more wavelengths or colors onto that single fiber. And it keeps increasing, but I've heard that you can put up to as many as 80 different channels onto a single fiber. And typically these are going to be more expensive optics because they're more precisely tuned. But they are better for longer distances or applications where you have to have more channels. And here's an example of all the different channels that you can combine onto a single piece of fiber using a DWDM type technology. So you can see fiber can be used for a lot of different things and a lot of different applications. And sorry I went a little bit long today, but if you'd like to learn anything about any of those different topics that we talked about, I think we've got individual classes for WDMs, fiber to the home, and some of the other basics that we have out there as well.